everyone, and welcome to our operating system laboratory experiment presentation. Today we will be demonstrating the fundamental concepts of process creation and management using the fork and X system calls. This presentation is brought to you by our team. We have Ajit Kumar SK, Amritavarshini M, Alfia J, Anushya K, Amrin AS, and Ashit Mohammed AR. The first system called the Explorer is fork. This is the primary way to create a new process in Unix-like systems. When fork is called, it creates nearly identical copy of the calling process. The new process is called the child and the original is the parent. The important part is its return value. It returns 0 to the child process. It returns child's process ID to the parent, and if something goes wrong, it returns a negative value. After the fork, both the parent and child execute concurrently, starting from very next instruction. Our first program demonstrates a simple use of fork. We will create a child process. Then that child process will use the X family of function to run the date command. Meanwhile, the parent process will simply wait for the child to finish and then display the termination message. Here is the step-by-step algorithm for our first program. We start the program and call fork. If fork fails, we print an error. If we are in the child process, we execute the date program using Excel. If we are in a parent process, we wait for the child to complete and then we print the termination message. Let's look at the code. After the fork, we increment a shared variable x. You can see the conditional logic based on the PID. The child prints its own ID, the value of x, and its parent's ID. The parent prints its own ID, the value of x, and the ID of its parent process, which is the shell. When we compile and run this, here is the sample output. Notice how the parent and child prints interleaved messages. Both report the value of x as 6, showing that child inherited the parent's memory state before the increment, and then both incremented their own copy. Crucially, the parent sees the shell as its parent, while the child sees the process with ID 298, which is its parent, as its own. Now, let's talk about X system called family. Unlike fork, which creates a new process X, is used to replace the current process memory space with a brand new program. It does not create a new process. The process ID remains the same. It's commonly used right after fork so that child process can transform itself into the different program. The example here shows Excel, which requires the full path to program and its name as arguments. Our second program combines fork and X. The algorithm is straightforward. We call fork. If it is the child process, we immediately use Excel to run the bin date command. The parent, as before, waits for the child and then prints a termination message. Here you can see the implementation using the switch statement for clarity. In the child case 0, we print child process and then call Excel. If Excel succeeds, the child process is completely replaced by the date program, and the line after it, like the P error and exit, will never run. They are only there in the case the X call fails. And here is the output. First, we see the output from our first program for reference. Then we run our second program, SC2. As you can see, the child process prints child process, and then the entire program turns into a date command, printing the current date and time. Finally, after the child finishes, which is now the date command, the parent wakes up and prints child terminated. In conclusion, we have successfully demonstrated the core OS concepts of process creation and program execution. Fork allows the OS to span new processes, while X allows those processes to run new programs. Understanding how parent and child process interact independently in the fundamental building block of understanding how modern operating system works. That concludes our presentation. Thank you for listening.